Yeah, I would like to say good morning. I would like to thank the organizers for the invitation to that wonderful place and the fantastic conference. I would like to report, if my slides are on the first scientific result from the neutrino mass experiment KATRIN, the Karlsruhe Tritium Neutrino mass experiment. I will give you a short introduction. I will explain you the experiment, and then I'm very happy to report about the first results before I give an outlook and conclude. Let me start. You all know from this conference how important neutrinos are. Unfortunately, with neutrino oscillations, we cannot measure directly the mass because neutrino experiments are kind of interference experiments and only allow to measure mass squared differences, not the absolute mass. But there are three complementary ways to the mass. One is cosmology. It's very sensitive. It compares power at different scales like CMB, large-scale structure, and so on. But it's model dependent, and its current sensitivity, if you believe in the cold dark matter model and the assumptions being taken, it's a 120 milli-electron volt for all three neutrinos. What is a big topic here at that conference is a second approach, the search for neutrinoless double beta decay, which requires Majorana neutrino, and thus it's model dependent, and we are discussing here at the conference also underlying nuclear physics problems. It's a wonderful process because you would not only measure the neutrino mass in some way, but you would be sensitive to lepton number violation processes. And the last one are direct neutrino mass determination, where you don't require further assumptions. You just rely on the relativistic energy-momentum relationship, and therefore m square is the observable in most cases. You could do time-of-flight measurements if you would have a very strong neutrino source and a very long distance, like neutrinos from a supernova, but that cannot be planned, and you have also underlying uncertainties from that. Therefore, these things are done typically with investigating the kinematics of the weak decays, like beta decays or electron capture processes, but you don't measure the neutrino because you measure the charge decay products and use energy momentum conservation to deduce the mass of the neutrino. I would like to compare the different methods because they do not measure the same. In the direct kinematic measurement, you measure m square, the so-called electron neutrino mass square, which is the real average and invariant sum of all mass eigenstates contributing with a mixing angle to the electron neutrinos. Whereas in neutrinoless double beta decay, you measure an effective mass, which is in coherent sum with all the CP and Majorana phases going in of all mass eigenstates contributing to the electron neutrinos. And of course, this formula has to be, there are some additional uncertainties which are not shown here if another particle is exchanged or the uncertainties of the nuclear matrix elements which we are discussing here. If you plot now for the normal ordering the cosmological relevant mass versus the mass from beta decay, then it's a one-to-one correlation for normal and inverted hierarchy, whereas for the double beta decay, there is this band, which doesn't include these uncertainties, but this band is coming from the unknown CP and Majorana phases going into the matrix. Therefore, one message, although neutrinoless double beta decay is so fantastic because it would allow to detect lepton number violation and learn about other things which are essential, like the baryon asymmetry of the universe, to measure the absolute scale, the cosmological relevant scale of the neutrino mass in the lab, you should do single beta decay. If you determine it from a beta spectrum, that is the electron energy spectrum of allowed or super allowed decay, it's essentially governed by the phase space of the two outgoing leptons, the momentum and energy of the electron and the neutrino, and there where the neutrino mass is in. This beta electron spectrum is a continuous spectrum, and at the very end, where the electron takes nearly all the decay energy and little is left for the neutrino is emitted non-relativistically, and then you can see its mass because the beta electron spectrum rises quadratically from the endpoint if the mass is 0 and deviates from it and stops earlier if the mass is non-zero. Unfortunately, that is a very tiny effect. even if you take the best beta emitter tritium, and if the neutrino mass is as big as 1 electron volt, that gray shaded area, which indicates the difference, is only 2 times 10 to the minus 13 of all decays. It's clear if you want to detect this, you need a very low endpoint, and I told you for beta decays, tritium is the best isotope. We will hear later in talks on Echo and Holmes that holmium is another alternative. Although it's an electron capture, it has a similar or the same phase-space shape at the endpoint. Tritium offers you a large decay rate because of its low half-life of 12.3 years. It has no shape uncertainties because it's super loud decay. Now, from the experimental side, you need a very high energy resolution to distinguish these two things. At the same time, a high luminosity, and this effect is so tiny, a low background. And for tritium, the best what you can do is a McGee filter, we will see later, or in holmium cryobolometers. Now, let me introduce you to the Karlsruhe Tritium Neutrino experiment at Karlsruhe Institute of Technology. It's a 70-meter long setup with a tritium source on the left and a big spectrometer on the right, followed by a detector. It's a windowless gaseous molecular tritium source. Tritium T2 is injected in the middle and freely streaming out to both sides, where it's pumped back. The whole system is a chain of superconducting solenoids. When tritium decays on their path, the beta electrons are guided with a huge acceptance to a tandem of a small and a big spectrometer. The decay rate in the source is 10 to the 11 decays per second. And after the pre-filter, which is a step filter which only allows the highest energies of electrons to pass, we have only 10 to the 3 electrons per second, which are analyzed with an electron volt resolution of the main spectrometer and are counted. The tritium flow here is retarded by 14 orders of magnitude by means of differential and cryogenic pumping. The whole experiment is being set up at Karlsruhe by an international collaboration of 150 people from 20 institutions from 6 countries, which you see here, and please see the happy faces of mostly young, very enthusiastic, very smart people, and a few seniors. Let me introduce you a little bit more into KATRIN. The windowless gaseous molecular tritium source is essentially a 10-meter long tube of 9 centimeter diameter embedded in a long chain of superconducting solenoids of 2.5 Tesla. The line is at 30 Kelvin. Tritium gas is injected in the middle and pumped back with an injection rate of about 5 curie per second, which gives us a column density of 5 times 10 to the 17 tritium molecules per square centimeter, which is about 1 of the reciprocal of the inelastic electron tritium scattering cross-section. By that column density, we are close to the maximum rate near the endpoint. The source is nearly opaque because we are at 90% intensity. If you consider that any inelastic scattering takes you so much energy away that you do not contribute to the count rate at the endpoint. We have to stabilize temperature, inlet pressure, and tritium purity to the per mil level to get a dynamically stable tritium source at the per mil level. Here you see a fisheye picture of the setup under construction. Of course, in reality, it's straight. On the upstream side of that source, there is a rear calibration and monitoring system consisting of a pulsed monoenergetic angular selective UV photoelectron source, which shoots electron into the beam. There is a rear wall with a very well-defined gold surface which controls the magnetized cold plasma of the windowless gaseous tritium source. And the whole system is seen by 2 big monitors which measure by X-rays the source intensity, and the rear wall can be illuminated by ultraviolet light for several purposes. Here you see some pictures how the system looks in reality. That is just the rear calibration and monitoring system. There's a second calibration system with a radioactive source, which we can inject more downstream. That is the cryogenic pumping system installation. You see how complex and nice it is. That is a picture of the laser Raman spectroscopy to measure online the tritium isotopes. And here we have some cold valves of our tritium source. That is followed by a tandem of two spectrometers of the McE filter types that are integrating high resolution filters, integrating with high energy path filters, which have a steps like function. Everything above a certain energy is let through, everything below is rejected, and the transmission, the solid acceptance is nearly 40%. The width of that step is of electron volt scale and is given by the ratio of the magnetic field, and that answers the question why the spectrometer is so big. It's a conservation of the magnetic flux tube. The whole spectrometer is at extreme high vacuum, 10 to the minus 11 millibars, the largest ultra-high vacuum vessel ever built. It's also on retarding voltage. Don't touch it, please. This retarding voltage of minus 18,600 volt is kept at the per mil level. Inside, there is a double layer wire electrode for background reduction and electric potential shaping. Outside, there's an air coil system for Earth magnetic field compensation and magnetic field shaping. And as I said, it's electron voltage resolution. Finally, the electrons which make it through the spectrometer are counted by a segmented silicon pin diode of 9 centimeter diameter with 148 backside segmented pixels. It's all with a thin dead layer and extremely high energy resolution dedicated for low energy electron measurements. The detector sits inside a superconducting magnet, and it's enhoused by an active and a passive shield. I told you all the nice things about KATRIN, this high luminosity, high energy resolution, but usually there are some drawbacks, and one drawback is that this McE filter type of thing is a little bit sensitive to all kind of backgrounds. We very well understand these backgrounds, and we have eliminated out of the 8 sources of backgrounds, most of them we knew beforehand, but some we had to learn new. We could eliminate or actively eliminate or avoid set up penning discharges, cosmic muons, which create backgrounds by the where we have this electric and magnetic barriers. But one source is left over, and I would like to show you what that source is. That source are led to 10 daughter ions implanted by radon-222 decays in the air during commissioning. That is everywhere there. And this radon, this lead-210, when it decays, it has a chance to eject highly excited neutral atoms, so-called Rydberg atoms, which can overcome our barriers of electric and magnetic fields. And they can be going through the spectrometer and on their way be ionized by the black body radiation of the spectrometer at 20 degrees Celsius. And then it freezes. It takes little energy. The infrared radiation of all these walls here would be enough to ionize, and then it freezes electrons which run down the electric retarding potential, and it's been detected here. That sounds crazy, but we really could show by several experimental means that this is the truth. For example, by field ionizing with changing the electric field on the wire electrode system, or by injecting artificially radon-220 source, which has only short-lived daughters. We did the same with radon-219, and then we saw the same kind of backgrounds, but this time it decays not with a 22-year half-life, but here with 10 hours half-life of the lifetime of the other daughter, lead-212. So we have several countermeasures. Some of them are in place, some others I will come back later. Now let's go on. We have now built a system. We want to commission it and check whether it all works like I told you. And one way is to use an artificial monoenergetic electron source, which is also emitting in 4 pi by a radioactive decay. And we use krypton 83M in a metastable state, which has 2 gamma transitions, which are highly converted. So we can measure such a sharp electron line of 1 electron volt width, a Lorentzian curve, if we convolute it with our transmission function of that integrating spectrometer, we get a little bit widened step-like function, which we perfectly can describe, and we can demonstrate that our system works at a 1 electron volt scale perfectly. Now that led us to do the final commissioning step with tritium to let tritium into our windowless gaseous tritium source, because there is no way to step back if something goes wrong. Therefore, we started with a small concentration of 1% DT in 99% deuterium to check the functionality of all components. With these two Nobel laureates and other very well-known people, Art McDonald and Takaaki Kajita, the experiment was started on the 11th of June 2018, just after Neutrino 2018 at Heidelberg. And we took a deep scan of the beta spectrum of 400 electron volts. You see here the background, and below the endpoint, the spectrum rises steeply. Please see the log scale here over several orders of magnitude. The error bars to be visible are enhanced by a factor of 50 here. And the residuals tell us that we can understand the spectrum right away. We didn't do this low concentration for the neutrino mass, but we were very happy to see that our tritium source is very stable. We require per-mole stability, and we even overdid in temperature. You see the temperature at 30 Kelvin is in the 10 to the minus 4 range. So in that pressure is better than the 10 to the minus 3 range. And also the tritium concentration, which we measured, is at the required level. You would say here we should improve a little bit, but please don't forget we have 1% DT, and usually we have 95% tritium, so this error bars will be shrinked by a factor of 100 if we run the real experiment. Now, in spring this year, the collaboration gathered together, and you see all these happy faces in the KATRIN control room, and we started to do a 4 weeks long measurement campaign with high purity tritium, 97.5%, which we determine online by laser Raman spectroscopy every 100 seconds. The tritium source was not at 100% nominal column density, only at 22, because we had some burn-in phases with radiochemical exchange reactions, but this gives us still 25 billion beta decays in the source. We collected high-quality data and did the full analysis chain using 2 independent methods. We did the first ever large-scale throughput of high-purity tritium in closed loops, which ITER still has to do, the worldwide fusion reactor. We run at 22% nominal density with high isotopic tritium purity. Here is a composition of our gas pumped in and taken back of 5 grams per day. Because of some burn-in phases of radiochemical reaction of T2 with the walls, we could not stabilize it to the per mil level, but at the percent level. But in our next runs, we have already demonstrated that we improved that to the per mil level. That is just a burn-in effect. We took 224 scans of the tritium beta spectrum. We have a retarding spectrometer where we set a retarding voltage, and we step through the retarding voltage in steps. That is an up scan, where we set every time a voltage, measure count rate. Here it's the endpoint, and then we measure in the background range 5 points. Then we go back and measure 22 high voltage points in the spectrum. That is a rate which we take in every step. Each scan takes 2 hours, and we repeated that 274 times. 40 electron volt into the spectrum, 50 above the endpoint. That is our measurement point distribution, which has these background points to determine the background level. Most of the time we spend where the neutrino spectrum is mostly sensitive to the neutrino mass, but we have to go deeper into the spectrum to determine the normalization and the tritium endpoint with the precision we need. Now, to analyze these data, we have to determine the response function, and that we do by shooting monoenergetic electrons from the electron gun through the column density and measure its spectrum in the spectrometer. And here you see one of these measurements versus energy above the retarding voltage. you see the step of the unscattered electrons. Then about more than 10 electron volts later, that is an inelastic scattering threshold, we see 1 time scattered electrons and 2 times scattered electrons. That is our response. If we really do the tritium, then it's a little bit different because tritium will decay all over the column density, and some of the electrons have only little column density to pass. Therefore, their scattering probability is smaller. This is about the same then for the electron gun, and this source is isotropic emitting. So we have to use our simulations to calculate the real transmission function, and that is just to check whether we understand everything in detail. It's not so easy to understand all the details, and we can turn by using time-of-flight methods this integral spectrometer in a differential spectrometer where we directly see with our eyes the inelastic scattering. If we pulse the source by a pulsed UV laser, it's a photoelectron source, we see that the time of flight on this axis depends on the surplus energy of the energy above the retarding voltage. That are the unscattered electrons which have this hyperbola-like just kinematic form where this time finally reaches speed of light. But we see the same structure about 12 electron volt lower because that is inelastic scattering, and we see these features. If we now do a cut on time of flights larger than 25 microseconds, we see the differential spectrum here of unscattered electrons, one-fold scattered electrons, two-fold scattered electrons with all the details. We can deconvolute the one-fold scattering. We see the molecular excitation, we see the dissociation peak, and we see the ionization tail with very great detail. We can now use this determined response function and convolute it with a theoretical beta spectrum and fit this by adding a background term to our data. And you see how nicely they fit. That is still a single run with 5 times enhanced error bars. Now, we got a high statistic of 2 million events in this 90 electron volt wide interval, 40 below the endpoint, 50 is of course only background. And we fit with 4 parameters, the m squared, the neutrino mass squared, the background rate, the normalization constant, and the endpoint value. I will come back to the endpoint value. We get an excellent fit with a good chi-square, a p-value of 0.56. And you see it here on the right, but still have in mind the error bars, just to see them, it's enhanced by a factor of 50. You see a constant background, you see a steep rise of the spectrum, and to get a feeling of the quality of the fit, the residues, the differences normalized by the uncertainty is shown here. We performed a bias-free analysis by blinding the so-called molecular final states. We did the full analysis chain first on purely Monte Carlo data. We didn't touch the real data, and only in the final states we've unblinded our analysis by unblinding the so-called final states and applied them to the experimental data. We did, for the systematics, 2 different analysis methods to propagate the uncertainties and infer the parameters, a covariance matrix method with a chi-square estimator, and independently by 2 different groups, set, and an independently Monte Carlo propagation and the likelihood estimators. I'm happy to report that both methods agree within a few percent. The neutrino mass and the endpoint are shown here. They heavily correlate, neutrino mass squared versus endpoint. You see the distributions here. And if we project down to the neutrino mass, we get a value. We fit neutrino mass squared unbiased. So although it's a physical parameter which is bounded by 0, it can only be 0 or positive. We fit it unbiased. That is done in the whole field. We could debate in the discussion later on whether that's the best method to do, but that is the most unbiased method. We get a 1 sigma negative result, -1 plus 0.9 minus 1.1 electron volt squared, and we get an upper limit of that of 1.1 electron volt if we use a very conservative Lokov-Chakov method. If we would use the more well-known Feldman-Cousins method, this would correspond to an upper limit of 0.8 electron volt at 90% and 0.9 at 95% confidence level. I showed you that this is very correlated to m squared to the endpoint. So we are here at a nuclear physics conference. We can now use our determined endpoint to check whether that is real. And we can turn by applying corrections for work functions and so on, and to recall our fitted endpoint, we can deduce the Q value out of that. The error bar still is very large because we haven't done some of the work function measurements in timely correlation to these measurements. And we can compare that to ultra-high precision panning trap measurements where the helium-3 and tritium atoms are measured, or ions are measured in a panning trap, and both agree very well, thank you, within uncertainties. All these results have been recently published in PRL and even made it to the front page, and some of you may remember that famous picture more than 10 years ago when that big spectrometer was transported to its final place when it went through that little village, Eckenstein, and you understand from that picture why the spectrometer is 10 meter in diameter and not a bit larger. This result brings us directly on the stage of that long tradition of tritium neutrino mass measurement starting in the late 40s. So we had an historic talk before. There is this history of tritium beta-decay measurement started in the 40s, and I should also report that was proposed by Enrico Fermi to do these measurements in 1934. On that Moore's plot, our first result fits well, but now we want to go down with a much steeper slope because we are aiming to take 1,000 days data, not only 4 weeks, within the next 6 to 7 years and reach a sensitivity of 0.2 electron volt or 0.35 if we see a discovery with 5 sigma. We have to improve still our signal to background ratio. We took in fall last year much more data in Science Run 2 with 83% nominal column density at a lower background rate. That is Science Run 1, the integrated luminosities that are calibration runs. And that is Science Run 2, which added a factor 3 more data. So we have a factor 4 data in hand compared to what I have shown. Still, we have to improve our background further. And one idea is the following. Our main background comes from these Rydberg atoms, which decay in all that volume. Of course, not completely equally distributed, but in all that volume. For the data taking I showed you, we have already shrinked the flux tube on cost of little energy resolution to a smaller volume to get our background. But since everything, that is the analyzing plane, the most negative electric potential, every Rydberg atom which is ionized on this side emits electrons to the source side. Every Rydberg atom ionized here emits it to the detector. That is counted to the detector. So we can shift the analyzing plane by the means of applying different potential to the wire electrode and running this air coil system differently, and we have even upgraded that to allow that. We can shift the analyzing plane farther downstream, and we get a more than a factor 2 signal to background improvement only by that measure at the same energy resolution. We did another spectrometer back out, and we will soon install liquid nitrogen supercooling by lowering the temperature below the 1 bar temperature to get a better radon 219 retention where the radon comes from our neck pumps. KATRIN is not only meant, thank you, for looking for the neutrino mass, it can also look for physics beyond the standard model. We are talking here at the conference also on sterile neutrinos, and because of the mixing of a sterile neutrino to the electron neutrino, it would be visible at an additional kink in the beta spectrum with a mixing angle. And for example, we discussed the reactor anomaly. It would be visible in a kink below the endpoint, and KATRIN can cover the most interesting range for that hypothesis. But it could also be sensitive in a dedicated run when we scan much deeper into the spectrum to KeV sterile neutrinos, which are nice candidates for warm dark matter. With having the best statistics of a super allowed decay, we can look for distortion in the shape and can look for non-standard model currents and additional light bosons and other things. And here you see some pictures of recent publications on these things. So KATRIN is very interesting for these things. For the KV sterile neutrinos to look for that kink, we would install a dedicated detector called Tristan, which is a highly segmented array of high-resolution silicon drift detectors. Let me conclude. I hope you are all convinced, and that's why you are here, that neutrino masses are very important for astrophysics and cosmology on the one hand, and for nuclear and particle physics on the other. KATRIN is the direct neutrino mass experiment complementary to cosmology searches, analysis, and neutrinoless double beta-decay searches. We have performed a first successful neutrino mass science run in 2019, yielding a limit already of 1.1 electron volt, improving by a factor 2 against all the former experiment. We are analyzing currently science run 2 with higher statistics, and we are preparing science run 3, which we will run with a significant lower background. We have the sensitivity goal of 200 millielectron volt for 5 to 7 years running. We can also look for sterile neutrinos and others. That is a recent publication, and there is a nice reading in the recent edition of the CERN Career. Beyond KATRIN, we can gain in statistics if we become able to turn the integrating spectrometer in a kind of differential spectrometer by applying a time-of-flight method or maybe a cryobolometer array. But that is maybe a little bit science fiction, but we are trying to do that. On the other way, there are very nice approaches, and we will hear two of them. One, the second talk after me, on Holmio microcalorimeters by the Echo and Holmes experiment. And there is a new idea around Project 8. Because of time reasons, I cannot report on that, but it's all interesting. So there's even a very interesting life beyond KATRIN, and I'm pretty sure that this field will finally find the neutrino mass. When I report about the first results, I would like to remember 3 very important founding members of KATRIN which passed away during the long road of KATRIN. Thank you for your attention.